now let's implement it in to C. So the idea is that, again, here I'm gonna use the GAN structures. Probably we can think the simplest GAN structure that we can think of. So here is a generator or discriminator. What do you think? What do you think? I mentioned that the GAN
it's a discriminator.
Yeah.
No?
Or number one consists of two networks, a discriminator and the generator. So number one, starting from latent space, in this case, is 100 neurons. And since we gonna use the MNIST data set, it's a 28 by 28. So we flattened out. So it's a 784 neurons. So it's at this, it's we are generating. And for this, the second neural net, it can take the inputs from generated or real MNIST data set. So it's a discriminator. Okay. And this is the structures that I'm going to use to implement it. Let me see. Okay, so you have X in this is real image from MNIST, and from latent code or space, it's passing through generator. This is generated image, and from over there, its discriminator should be say this is like it's 1, because I'm saying 1 is real, 0 is fake. And for this part should be for discriminator should be zeros. But for generator, this should be for generator for right. That was the main idea that we discussed a lot last time, if you remember. So say we have input and outputs in input outputs for discriminator and the generator, and hidden layers for discriminator, another hidden layers for generator. So this will be the number of neurons from this designed the GAN structure that I proposed. So this part for discriminator and this one for generator. So again, it's 100 dimensions and 784 images. Now we need to define the loss functions for discriminator and generator at the same time. Okay. Then after that, we need to like apply the gradient descent to optimize it. For loss, we have two losses. One is for discriminator again, for discriminator and for generator. So for discriminator, this is the objective functions. And how do you get this one? Probably you have to take a look at the previous lectures or slides that I provide. For discriminator, we have this part is just coming from, and this one is, and we put minus because it's minimization problems. The original was, I think it's, if you remember, this maximization problems, but I put minus sign in front of it so that I can convert it to minimization problems. So if you get real data, the reals, and this one is the fake. That's how we define loss for discriminator. And loss, on the other hand, loss for the generator is this one. So this is fake. And now, once we define it, when you apply the gradient descent here, this means we're gonna okay. So we have two optimization functions. Both of them gonna add on optimizers, but I want to minimize the loss first. Then the generator will be like a back and forth. I will do gradient apply the add-on optimizers for discriminator first. So as you can see, the variable list, this is the only list that we allowed to update it. So it's the variable list. So as you can see here is from these are the only the TF variables that I'm going to update for discriminator. And for when you optimize the generators, this will be the generator variable list. So as you can see, right? So when you do optimization on discriminator, I'm gonna fix the values for generator because I want to maximize the discriminator first. On the other hand, you want to optimize, when you try to optimize generator, I'm gonna make all the decision variables or TF variables related to discriminator, keep that constant or keep that fixed. That's the idea. So now we have placeholders of there, Z, and the X is this is another placeholder for the real. This one is for real, and this one is for fake to generate noise first. Then during the generators, we're gonna generate fake MNIST data set or image. Again, as you can see here, when you optimize it, discriminator generators are separately trained. So we have, so this one is like we will do iterations. One by one. So let's do the discriminator first, and we're gonna do generator next, and we're gonna repeat it. For generator, only thing that we need to the placeholders, it's a noise, like a state latent space. For discriminator, we can take the input from the true values from the training data set, or starting from generator like that. So it's from noise on it. So this is how we implement it. Okay. Now after we trained, so again, if you remember, this GAN is one of the model for generative models. So after that, we're gonna use generator only to generate the new data set. We don't need discriminator anymore, right? So we don't need this. So only thing is we need generator. So we generate the random samples for the latent space, and we do 4 propagations to get the generated MNIST data set. So how do you do? So we're gonna make noise on it and put the noise in the Z placeholders. There will be the output image or MNIST data set. And this is kind of one of the examples that we can generate it. Let me, I can show this one. This is the generated image on it. I mean, for our case, you have, I mean, you have to think of like most students gonna run the GAN in CPU based, not the GPU. So we cannot make complicate the examples here. But this one, if you progress, this one is over there. This is 20 by 28, but this one is like this. So think about the complexity, and if we do, let me see. So this one is generated images. Can you guys can believe? This is not real. These are the pictures that we are looking at. They are fake, right? You did from NVIDIA.
Oh, this is disturbing.
This one is even I cannot believe. I cannot believe. Okay. And let's see up there. I was trying to run this one, but I found some. So if I run it, somehow I some like the kernel is dead. So I don't know what's. Oh, let me see. It's running or dead kernels. Looks like it's running it. So let me then, while we are waiting, let's see. It's gonna take a lot. So don't run it in CPU based. Probably you can use the Colab that I introduced in the previously. So that was you can use the Google GPU resources if you want. Over there, let me see, got it. And this is the shape of this one. And weights and bias, we need to define it. And the generator and discriminator, I made it as functions. And as you can see, it's get inputs and hidden. For this is generator, so I'm talking about this one. And discriminator, we will get the inputs and hidden inputs and hidden layers and output layers. And make noises, you can see is from over here, it's a latent space. It's a Gaussian or normal distributions, literally. So it's make kind of latent. I mean, I don't like the name of make noise, the name of functions, but you can think of as a latent space. We do random sampling. So from Z, we can generate it and we can put into the discriminator, right? Then it will be fake images. And I mean, it's from this one will be deep fake. And for discriminator, if you put X is the placeholder for the true MNIST data set, so it will be real. And now I define the loss functions for discriminator and the generator respectively. And this will be the only weights and bias for D and for generator. And now again, you have two different optimizers. We need to define it because they have two different losses and trainable weights. And if I run it, so okay. Now we run right now you think I think this is like 3 and this is either 6 or 8. I mean getting close. I mean this is like see like initial is totally random, but somehow somehow after 5,000 iterations and like 10,000, and you know, it's looks like around this one is, what do you think? This one 9, 4, I don't know. This one is like 8, and this is like 3. It's still running even in the GPU. Even though I'm using GPU. Oh, I got another one. What do you think is 8? Another maybe 0. I don't know. So in 50,000, that's the maximum number of iterations that I set. This one I don't know. I can stop here, and this is the let's see. Once we after training and make noise and put the noise into the generator so that I can. So this one is the image that is. I interrupt in the middle of training process, but it's okay. So don't worry about the quality of the outputs, but now I run it again, generate another, make noise on it. Like in this image that you are looking at does not exist in a world. It's something that the GAN or I created. All of them are generated and fake. What do you think? This one is 1 or 7, I guess. This one, I don't know. This one, 6. 3, maybe. 0, maybe. 9. So what do you think? Do you think this GAN works or not? But as you can see, one of the problem, I make noise, right? And put it here. I'm not able to control what kind of digit that I'm going to generate. As you can see, now it's like, right? But in many cases, a lot of people want to, hey, I want to create the GAN. I want to do GAN to generate, let's say, 5, digit 5 or digit 6. I want to control something. I have control on what kind of digit that I want to generate it. All right. So that's why the next topic or motif or motivation is now is conditional GAN. I want to add conditions in a GAN. Does it make sense? So probably at the end, what I want to say is, hey, GAN, I want you to generate zeros, bunch of zeros, bunch of 9s. Right? So that's the topics that I want to do. It's a more advanced one is a conditional GAN. Let me explain what it is. Unconditioned these are the GAN that we just studied it. There is no control on like data being generated. Right? You can think of mode or labeled or conditions. We don't have any control on that. But on the other hand, so like people that generate conditional GAN or CGAN, the generator learned to generate fake samples with the specific conditions or characters, whatever, rather than generic sample from unknown noise distributions. So what I want to do, so now it will be, these will be conditions. Again, as you can see, it's one hot encodings. Okay. And this is conditions, and I want to do, so I want to generate like bunch of zeros, bunch of ones and twos, and this is what I want to do. So this is the structures. And now let me explain step by step. How do I say? Let me read. Let me. What I want to do. Say this is discriminator and X real, X fake, and we do have generator and Z noise. This is the GAN, and this will be CGAN. Okay, so let's see the difference that we have to let either both generator and discriminator, they let they know what kind of labels they want to generate, what kind of conditions. So it's a, let's say it's label and condition, and in this case it's a class. So it's a, so we need class informations. So see, we have to tell generator, so that like a generator can we're gonna generate what they, we're gonna tell the generator say what kind of digits they want to generate it. And for discriminator, we should let discriminator know. We should tell discriminator, hey, the image that you are looking at is say like 0, and now it's, we made the scope is narrowed down. So you're gonna for discriminator, you're gonna tell that you're gonna see zeros, but you have to differentiate it whether this is real zero or real looking fake or generated zeros. And and you have to know. So we will pick it. We will pick in the training data set, and so we have to know. So these are the, I mean, it's conditional GAN, right? Now it's same, right? Again, here it's a simply modifications from the original GAN to make conditional GAN or CGAN. So the only, so from starting from the original GAN, I'm gonna add the, here is class or labels, and that make these kind of connections to do it. So to visualize this, says in the latent space, in many cases, we're gonna use uniform distribution or Gaussian distributions. And suppose we use Gaussian distributions from the previous MNIST data set, I use 100 latent space or latent code, but just think about, say I'm gonna only use 2 to visualize, to get some insight on it. And for the generator at the original GAN, we're gonna do random sampling. Suppose we got the same data points from here, then from generator, probably we're gonna generate like digit of 3. And if we take something over there, we're gonna take the 6. And from there, we're gonna take another digits. That's what the generator does. For conditional GAN, it's a little different. Because for generator, we're gonna tell what kind of digit they're supposed to generate. So this one is like from this one, and with this one we'll get 1. From these data points and 3s, we'll get 3s. All right. So feed random point in the latent space with the desired numbers or class or label. So the idea is even if the same latent points, we're gonna use, will be used for different numbers. And what the physical meaning of now it's in the latent space, you probably hear, I don't know what it is, but say it's like how much the number is tilted, like that. Or height, how, or probably here in the same locations, probably like how thick. Now it's in the latent space, the location of latent space is gonna be related to the pattern of or shape or whatever, like how much rotated or tilted and thickness of lines and things like that. Now in the physical meaning of latent space is now it's little because now you don't have to remember what kind of type or what kind of desired numbers because it's gonna be given from the conditions. So let me see. Now it's labeled, it's not encoding, so it's like 10 at neurons. So here we have 10. We have we original GAN was we use in this case I don't know why, but now it's 128. Change it. Probably it doesn't matter that much. Okay. Now let me see. For generator now we need inputs and the labels. So we need to add these two. Okay. For discriminator again, for discriminator we need these two. So it will be again it will be input and labels as well. So here over there is just if once we have this kind of structures, this is just I think it's super easy it's just straightforward. Now we had another placeholders for class or label. For generator and discriminator, and let me think. Now we need to take the label as well. For discriminator, we need to take the label as well, so as you can see. And for hidden layers, the only difference is over there. We need to concatenate it, the input labels. For discriminator as well, we need to concatenate it and the input and labels. For CGAN, for conditional GAN. And the rest of them, I think it's pretty much the same. And for discriminator, now we have input and X and accents. This is fake generated one and the class, and this is real one and class. And for the generator, it's the noise and the class as well. Now, this is how we implement it. For again, is for the optimizations we need to add the class as well. In order to generate the fake MNIST data set using the CGAN, we need to feed noise and the class as well. Okay. That's the only difference. I think once I believe that once you fully understand the structure of the original GAN, it's not that difficult to implement and understand the conditional GAN or CGAN. So let me move on to over there is condition GANs, and let me try to run again. So this is how we implement the conditional GAN. I think it's for conditional GAN, it's a lot of I think have opportunity for a lot of different engineering applications that. So that's why I spent some time to share the idea of conditional GAN. So let's for this one, let's stop here and suppose that I didn't. Let me see. So now is now what I want to do. So if I feed noise with this one, what kind of digit are you supposed to see? Like what kind of digit is supposed to be generated? You guys know what I'm talking? It's one-hot encodings. 0, 1, 2, 3, 4, 5. So let's see. Do you think this is 5? I can generate like a lot of 5, but I think don't worry about the quality of the generated image. But and let's try another digit. Give me any digits that I can try that you guys want me to try.
8.
8, then choose. There will be 9, or so this one will be 8. I think this is, I mean, looking awesome, great. I think this one is good. All right. So that's what the all about the conditional GAN or CGAN. And other tutorials I posted a lot of. Let me see. This is the guy. Yeah, good fellows. This is the guy that invented GAN structures in 2016, and this is the. And let me see this one. And this one is the generative models that from Stanford University, and another one from MIT, and another one from University of Waterloo, and things like that. So if you interested and to want to know more about the GAN, probably you guys can take a look at the video clips or online lectures that I provide. And if you Google it and like Google in YouTube, and you guys can find a bunch of them, and most of them are useful.